The universe doesn't exist. What if the universe you trust doesn't exist the way you think it does? Not a magic trick, just physics pulling the rug on our assumptions. 3 lenses do it. A holographic universe where the boundary encodes the bulk, a possible simulation, and a version of quantum gravity where time itself doesn't fundamentally exist. The proof trail runs through black hole math, quantum information, and even error-correcting codes that seem to hold spacetime together. By the end, reality will look different, grounded, not woo. And there's one experiment that flips the whole story. Stay for that. If any part spikes your curiosity, pause and comment your question. Your best why might make the next episode. Let's get straight to the foundations. What doesn't exist actually means. Okay, so here's the thing. When I say the universe doesn't exist, I'm not denying tables, stars, or the feeling of Monday morning. I am challenging naive realism, the idea that the world is exactly as it appears and that our everyday picture is the bottom layer. Quick gut check. What's the one thing you think must be fundamentally real? Hold that thought. We're going to test it against the data. Most people think real means mind-independent stuff with definite properties. But in modern physics, real comes in layers: ontological, emergent, and effective. That's the first unlock. Ontological means fundamental. Whatever the deepest theory says cannot be reduced further. Emergent means patterns that are stable and causal even if they're not the base ingredients. Effective means a model that works within a range, like Newtonian gravity at low speeds. Air is an emergent fluid. Its realness doesn't vanish just because molecules are more basic. The claim here is similar. Space-time, particles, even time might be emergent or effective, real for us, not fundamental. Now map the models. Classical physics gives you objects with positions and momenta, evolving in time. Quantum mechanics swaps that for wave functions and probabilities where measurement outcomes are contextual. General relativity says spacetime is dynamical geometry. Quantum field theory says particles are excitations of fields. Then information theory enters. Maybe the most basic description isn't stuff in space, but relations and bits, entanglement, symmetries, and states. Different maps, overlapping territories. Language traps us fast. We toss around words like fundamental, illusion, and real as if they're simple. Illusion doesn't mean fake. It means what you experience isn't a direct readout of the base layer. A rainbow is an illusion in that sense. Light, droplets, and geometry produce a stable phenomenon that looks like a thing. It's robust, predictable, meaningful, and not a standalone object. That's the flavor of doesn't exist we're dealing with. Here's why that matters. If spacetime is emergent from quantum information, then asking what is space made of is like asking what is temperature made of. It's made of microstates and statistics. Temperature exists, it's just not the micro-level thing. Same with particles. They are effective excitations that disappear or transform under different energy scales or dual descriptions. This is why physicists care about dualities. 2 wildly different pictures can describe the same physics. That should make you cautious about treating any single picture as the thing itself. Quick micro story. Last week a viewer DM'd me. I had deja vu. Does that prove quantum multiverses? I get why your brain jumps there where pattern matches. But deja vu is a memory phenomenon, not a physics signature. Separating hype from physics means this. We let the math and experiments lead, then carefully translate. If a claim doesn't cash out in predictions or precise statements, it's not helping you understand, no matter how cool it sounds. If you've had a physics feels weird moment, drop it in the comments and stress test it. Best ones get featured. So what's the workflow? We use models that predict experiments. We test where they break. When a model fails, we don't say reality is broken. We say our description was limited. And then we upgrade. Doesn't exist becomes that layer is not fundamental. Its rules come from deeper constraints. That mindset keeps you honest and curious. Now, why do physicists suspect the everyday picture isn't fundamental? Because it breaks at extremes. Black holes, the early universe, and quantum scales. Your intuition says the number of possible configurations inside a region should scale with its volume. But black hole thermodynamics screams the opposite. The information content scales with area. That's not a detail, it's a siren. Everything changes when area, not volume, counts. And here's where the trap springs. If the maximum information in a region depends on its boundary, not its interior, then the interior story might be a compression, an efficient description derived from boundary data. That's the seed of the holographic principle. Real bulk physics could be a rewriting of boundary information. It doesn't make your chair vanish. It reframes what it is, a stable pattern in a deeper bookkeeping. Most people think that makes reality flimsy. It doesn't. Emergent structures can be insanely robust. Think of software abstractions. You type in a doc, not ones and zeros. The interface is real for you because it controls causal power at your level. Same with spacetime if it's emergent. You can navigate with GPS and launch rockets. It works because the emergence is consistent. So to see the trap clearly, start where reality breaks first. Black holes. They force the math and the math forces the hologram. That's our next step. Black holes force the hologram. Start with the weirdest bookkeeping rule we've ever found. Take a black hole. You'd expect its information content, how many distinct internal states it could have to scale with its volume. More space, more possibilities, right? But the Bekenstein-Hawking formula says the entropy, which is a proxy for information, goes like the area of the event horizon. S equals the horizon area divided by 4 in Planck units. Area, not volume. That's the alarm bell. Mental sticky note. If area counts, your intuition about more space equals more info is about to get humbled. Here's why that's so disruptive. Entropy measures the number of microstates consistent with what you can access. For ordinary stuff, a gas in a box, it scales with volume. Double the box, double the possibilities. But for a black hole, doubling the radius quadruples the area, so the entropy scales with area. That suggests the maximum number of distinguishable states inside a region is proportional to its boundary. Your gut says no. The math says yes. Now the information problem. Toss a book into a black hole and wait. Hawking's early calculations showed black holes radiate like hot objects and evaporate. The radiation looked thermal, random. If the final state is just featureless heat, where did the detailed information about the book go? If it's destroyed, quantum mechanics breaks because the evolution of quantum states is unitary. Information is conserved. That's a foundational rule. So either unitarity fails, or we're missing something critical. This sparked decades of debate. Stephen Hawking initially argued information is lost. Leonard Susskind and others pushed back hard. Unitarity must hold, even if it means reshaping our picture of spacetime. The eventual consensus among many theorists is that information is not destroyed. Hawking later conceded. But that raises the how. If nothing escapes classically, how does the information get out? The holographic principle is the clean rescue. It says the physics inside a region can be fully encoded on its boundary with no loss. Think of it like a hologram. A two-dimensional sheet contains the information needed to reconstruct a three-dimensional image. In our case, the boundary, roughly, the horizon area, counts the degrees of freedom. The interior, the bulk, is an emergent description. That reframes the evaporation puzzle. The information can be stored in boundary degrees of freedom and leak out in subtle correlations in Hawking radiation. But here's where it gets interesting. Holography isn't just a metaphor. It predicts a literal cap on the number of independent states a region can have. The Bekenstein bound. Try to stuff more, you collapse into a black hole and the area stops you. So the universe enforces an information budget based on surfaces. That budget is what pushes us toward a boundary-first description. Your intuition fights this because we're used to volume scaling. Let's do napkin math. Imagine packing 1 bit per cubic Planck length in a sphere. That's volume scaling, huge. But a black hole of that radius has entropy proportional only to the surface area. If you keep stuffing bits, gravity says no. The system becomes a black hole with a horizon that encodes at most area over 4 bits. Gravity overrides naive counting. Your gut is wrong because gravity couples energy and geometry. Now, what about the interior story? If the boundary encodes everything, then the bulk fields and geometry are like a compressed file that unzips when you use the right dictionary. That's the holographic principle at work. Bulk physics is a redundancy-free recoding of boundary data. Locality in the bulk, nearby points influencing each other, emerges from patterns of entanglement and constraints on the boundary. Fewer true degrees of freedom than volume suggests is not a bug, it's a deep simplification. Return to the information problem. If evaporation is unitary, where's the mechanism? The modern view is that Hawking radiation isn't perfectly thermal. It carries long-range, almost imperceptible correlations that, in principle, encode the infalling information. Page's curve, named after Don Page, predicts how the entanglement entropy of radiation rises then falls as the hole shrinks, consistent with information recovery. Recent gravitational path integral techniques even reproduce Page's curve using replica wormholes. The point, with holographic thinking, unitarity and gravity can coexist. But I want to stress limits. The holographic principle is a general idea, motivated by black holes and crystallized in precise dualities in special spacetimes. It doesn't mean our universe is literally a movie on a screen. It means the number of independent bulk details is bounded by a surface, and that a boundary description can, in some cases, be fully equivalent to a bulk one. That's a radical reduction in what inside means. So, what's the intuition shift you need? Stop treating space as a warehouse of independent cells. Start treating it as a code book where most apparent degrees of freedom aren't independent at all. The area law is the signature of a highly entangled, highly constrained system. The interior is a story that the boundary can tell efficiently. One more thought. If you accept that the boundary can encode a universe, then you should ask, can we ever see the dictionary in action? That's where we're headed. There's a concrete case where the math is explicit and checkable. It's not our cosmos, but it shows the principle isn't hand-wavy. If a boundary theory can exactly reproduce a bulk with gravity, we'll have a working lab for holography. Okay, if a boundary can encode a universe, can we make it concrete? Yes, and it's time to meet the duality that put holography on firm ground. Add SCFT, a universe on its edge. Here's the concrete version. In 1997, Juan Maldacena proposed a duality that stunned everyone. A gravitational theory living in a space with constant negative curvature, anti-de Sitter space, or ADS, could be exactly equivalent to a quantum field theory without gravity on its boundary. That boundary theory is conformal, so we call it a CFT. One universe with gravity inside, one gravity-free theory on the edge. Same physics, two descriptions. If you love two truth, one reality moments, this is your section. Why does that matter? Because it turns the holographic principle from a bold idea into a working dictionary. You can compute something on the boundary CFT, say, a correlation function, and translate it into a statement about particles moving and fields vibrating in the bulk ADS, or do the reverse. Start with a bulk process and read it as a complex pattern in the boundary fields. No hand-waving, actual equations match. Now, this is important because it shows boundary encodes bulk isn't metaphorical. In Add SCFT, bulk locality, geometry, and even black holes emerge from the entanglement structure and operator relations of the boundary. The mapping is precise. Bulk fields correspond to operators in the CFT. Bulk masses and charges map to scaling dimensions and symmetries. Distances in the bulk relate to how quickly correlations decay on the boundary. The upshot is wild. Gravity becomes a story told by quantum bits on an edge. The real secret is how space shows up. Enter the Ryu-Takayanagi formula. It says the entanglement entropy of a region of the boundary equals the area of a minimal surface in the bulk that hangs off the region's boundary, measured in Planck units. That's a direct area law linking information to geometry. When the boundary state changes, more or less entanglement, the minimal surface reshapes, so the bulk geometry morphs. In short, entanglement patterns write the shape of space. Everything changes when you realize this is not just a trick for pure states. The quantum-corrected version, FLM, and then the quantum extremal surface prescription adds bulk entanglement contributions too. That tightens the bond. The dynamics of spacetime aren't arbitrary. They're constrained by how information is organized. Gravity and information theory are speaking the same language. Let me show you the intuition. If boundary regions A and B are highly entangled, their corresponding bulk regions sit close in the emergent geometry. Reduce entanglement and the bulk neck between them thins. Cut it enough and the bulk can disconnect. That's geometry responding to information, not the other way around. It's why people say spacetime is a compression of quantum bits. You might ask, but our universe isn't at S, it's closer to de Sitter, positive curvature. True. The duality is cleanest in AD-S, especially with supersymmetry and large N-gauge theories like N=4 superYang Mills. That's a limitation, but we can still transfer key lessons. First, area law entanglement ties to geometry is robust, seen in many-body physics and tensor network models. Second, unitarity and gravity can coexist via a boundary description. Third, black hole thermodynamics fits naturally. The boundary accounts for microstates, and bulk horizons track entanglement surfaces. Here's where it gets interesting. The AD-SCFT dictionary works like a bilingual glossary. Bulk fields left-right arrow boundary operators. Bulk isometries left-right arrow boundary conformal symmetries. Bulk radial direction left-right arrow energy scale on the boundary, which is the renormalization group. That last one is huge. Moving inward in the bulk is like zooming out the energy on the boundary, coarse graining. Geometry is renormalization made spatial. A quick micro-clarifier. When people say the boundary has no gravity, they mean the CFT is an ordinary quantum field theory on a fixed background. The gravitational degrees of freedom live in the bulk. Yet every gravitational effect, from light bending to black hole formation, has an image in boundary correlation functions and states. That's equivalence, not resemblance. Now the payoff. If space is made by entanglement, what builds time? In AD-SCFT, time is a parameter in both pictures, but the way bulk dynamics arise is through boundary Hamiltonian evolution. The bulk happens because the boundary state evolves. In fact, some proposals suggest that the arrow of time in the bulk links to entanglement growth under unitary boundary dynamics. That's not the final word, but it's a sharp clue. Temporal order may also be a higher-level pattern of information flow. Before we get carried away, a caution. Not every bulk operator can be reconstructed from every boundary region. There's an entanglement wedge. Given a boundary subregion, you can reconstruct the bulk region that's causally tied to it in the holographic sense. This is where quantum error-correcting codes enter. AD-SCFT behaves like a code. The same bulk bit can be redundantly reconstructible from different boundary subsets. That redundancy makes the bulk stable against local boundary noise. Why should you trust any of this? Because it predicts things we can check within the duality. For example, thermal states in the CFT correspond to black hole geometries in the bulk. You can compute entanglement entropies, mutual information, and see geometric transitions, exactly matching predictions from gravity. Multiple independent calculations agree. It's not marketing, it's math locking into place. If this clicked for you, tap like so the algorithm knows to serve you the deep cuts, not the fluff. So yes, our cosmos isn't AD-S, and future work must handle cosmological horizons and positive curvature. But the core insight stands. Geometry is a bookkeeping for entanglement, and gravity emerges from quantum information organized by symmetries. If space is woven that way, the next question is obvious. If space is made by entanglement, what builds time? Let's go there. The death of time in quantum gravity. If space can emerge from entanglement, what about time? Here's where quantum gravity throws a curveball. In our best attempts to quantize gravity, the master equation doesn't even have a time variable. The Wheeler, DeWitt equation looks like h acting on the wave function of the universe equals 0. No T, no ticking. That's not a typo. It's the statement that, at the most fundamental level, there's no external clock to measure change against. Quick challenge. If now isn't fundamental, what's the last moment you can prove existed without using your memory? Post your best answer below. Now, this is important because all of physics normally runs on time evolution. In quantum mechanics, the Schrödinger equation tells you how states change with time. In general relativity, time is part of the geometry that bends. When you try to merge them, time refuses to be a universal backdrop. It becomes relational. Change is only meaningful compared to other change. So what we call time might be a bookkeeping device emerging from correlations inside a timeless whole. The Page-Wooter's mechanism shows this cleanly. Take the universe as one giant entangled state. Split it into two parts, a clock and the rest. Globally, nothing evolves, it's static. But if you condition on the clock reading, what's the state of the rest when the clock shows tau? You recover ordinary time evolution for the rest subsystem. Time appears internally from entanglement with a subsystem that behaves like a clock. No external parameter required. Everything changes when you realize you can swap clocks. Choose a different subsystem as your clock and you get a different relational time. That sounds odd, but it highlights the point. Time is not an absolute river. It's an order you infer from correlations. The thermal time hypothesis pushes this further. Given a state of a system, there's a natural flow, the modular flow picked out by the state itself. In other words, the state defines its own time. That's radical, but it aligns with the idea that dynamics live in the structure of information. My watch still ticks, right? And there's a reason. At macro scales, with lots of degrees of freedom and stable arrows, different relational times align to a common effective time. That's because big systems have robust coarse-grained descriptions. Entropy gradients and decoherence make certain variables behave like reliable clocks, oscillations of atoms, planetary motion, atomic transitions. The emergent time you live by is the consensus view that comes from averaging over microscopic fluctuations. Let's make that concrete with a micro story. Years ago, I spent a day in a windowless lab calibrating detectors. No sunlight. No cues. After a few hours, my sense of how long went weird. But inside the lab, the equipment had internal clocks, count rates, oscillators, perfectly dependable. My internal sense drifted. The relational clocks in the apparatus did not. That's the split. External markers can vanish, yet internal correlations still anchor an order of events. Now arrows. Even if fundamental dynamics are timeless or time-symmetric, we experience a one-way flow. Where does that come from? Entropy. Start with an unusually low entropy macrostate, the past hypothesis for our universe, and typical evolution leads to higher entropy in both time directions from that special boundary. But we're on one side of that low entropy boundary, so we see records accumulate, glasses shatter, coffee cool. Decoherence cements this arrow locally. Interactions with the environment wipe out delicate phase relations, stabilizing pointer states that look classical and remember the past better than the future. There's another clue from holography. In AD-SCFT, the boundary Hamiltonian generates evolution. Bulk time is encoded in boundary dynamics, and entanglement growth tracks geometric growth. Quantum extremal surfaces shift as states evolve. Areas change with information flow. So even in a timeless Wheeler, DeWitt sense, a notion of before and after emerges when you slice the universe into subsystems and choose a clock degree of freedom that evolves relative to the rest. You might be thinking, if time isn't fundamental, does causality fall apart? It doesn't have to. Causality can be an emergent constraint about which correlations are physically realizable. In the bulk, light cones and no signaling arise from the structure of the emergent geometry. On the boundary, microcausality, the vanishing of commutators outside the light cone, keeps cause and effect intact. The relational view respects these constraints while admitting that the global, timeless state contains all correlations at once. Actually, wait, there's a subtlety. If the global state is static, why does anything look like it changes? Because you're a part of the system. Your memory is another set of degrees of freedom. Change is the progression of brain states correlated with other records in the environment. Your narrative of time is the unfolding of correlations inside a high-entropy, decohering universe. That doesn't trivialize experience. It explains why it's so consistent. So where does this leave your watch? It's a great clock because it couples to degrees of freedom that are stable, periodic, and weakly perturbed by noise. Those properties don't require fundamental time. They require regular dynamics under coarse-grained conditions. That's why precision quantum clocks can detect tiny gravitational time dilation. Effective time still bends with geometry, even if both are emergent from deeper relations. No time at the base sounds unsettling, but it's a feature, not a failure. It frees us from forcing a universal clock onto a theory where geometry and energy are intertwined. It suggests that what we call the present is a local slice through a web of correlations, not a cosmic metronome. And it points to a cleaner anchor for causality and dynamics, information. No time, then causality's on thin ice, unless information steps in. Reality as information. Okay, so if time can be relational and space can emerge from entanglement, what's left underneath? Here's the cleanest bet: information. Call it from qubit. Not rocks and fields first, but states and relations, bits and qubits, out of which rocks and fields are built as stable patterns. If this reframes how you think about stuff, share it with the one friend who argues that only matter is real. Let me show you why this isn't just a slogan. In AD-SCFT, bulk spacetime behaves like a quantum error-correcting code. That's not a metaphor. The mathematics mirrors codes we use to protect qubits in real quantum computers. In a code, you redundantly spread information across many physical carriers so that local errors don't kill the logical state. In holography, a single bulk logical qubit can be reconstructed from multiple overlapping boundary regions. That redundancy explains a mystery. How can the bulk feel local and stable even when the boundary is noisy? Because the bulk is encoded. Local boundary disturbances act like correctable errors. The logical geometry survives. This is important because it ties stability to structure, not stuff. Spacetime smoothness is the symptom of a well-designed code. The entanglement pattern resists small perturbations. Tensor network toy models, like HOPPY codes, make this explicit. A tiling of perfect tensors maps logical bulk degrees of freedom to many boundary legs, implementing exact error correction. Change which boundary pieces you hold, and you still recover the same bulk operator within an entanglement wedge. That's bulk reconstruction in action. The boundary doesn't just store the world, it can selectively rebuild regions of it. Now, what does reality as information actually buy you? First, a mechanism. If the boundary state and its Hamiltonian evolution specify all observable correlators, then the bulk phenomena you care about, matter falling, light bending, horizons forming, are compressions of boundary correlations. Events in the bulk are, at root, facts about what can be reconstructed from which boundary subregions. Causality becomes a constraint on which reconstructions are consistent, enforced by entanglement structure and symmetries. Second, an accounting rule. Landauer's principle says erasing one bit of information costs kBT ln2 of energy dissipated as heat at temperature T. That's a lab-tested law. Information isn't abstract bookkeeping. Changing it has a physical price. Flip that around in gravity. Horizons have temperatures and entropies, so moving, hiding, or revealing information across a horizon shows up as energy flows and geometric response. When you accept that, thermodynamic-looking gravity stops being surprising. It's the energy budget of information processing across causal boundaries. Third, a clearer story of matter. Why does a table feel solid? Not because tiny billiard ball particles are jammed together, but because fermionic fields and electromagnetic interactions create stable, gapped excitations with exclusion principles and low-energy effective behaviors. Solid is a macro-level code word for an array of constraints Symmetries, statistics, band structures that lock in reliable responses. You push, it pushes back. That consistency is informational. Given inputs, the system returns predictable outputs because its microstate ensemble obeys tight rules. The solidity you feel is the interface of an error-corrected, decohered, coarse-grained world. Let's talk reconstruction for a second. In holography, bulk operators deep inside can sometimes be written as different boundary operators depending on which region you access. That sounds like ambiguity, but it's code redundancy. Multiple boundary encodings of the same logical bit. Lose part of the boundary and you can still decode from the rest, as long as you hold enough. That's why entanglement wedges belong to boundary regions. Ownership here means reconstructability, not possession. You might ask, if everything is information, who's doing the computing? Careful, that's the trap. Universe's computation doesn't require an external programmer or a cosmic laptop. Computation can be intrinsic. State evolves by lawful transformations. Structures implement algorithms by their dynamics. A cellular automaton is computed by its rule, not by a person pressing run. Likewise, a Hamiltonian generates evolution without anyone supervising. The stronger claim worth taking seriously is this. Physics is the study of constraints on possible states and transitions, i.e., on information and its flow. That's different from we live in a teenager's video game. There's also a practical angle. If spacetime and fields are encodings, learning the code family, its symmetries, redundancy, and correction thresholds, tells you where geometry is robust and where it can tear. That matches findings like entanglement phase transitions, change couplings or measurement rates and reconstructability jumps, mirroring connectivity shifts in bulk-like models. Cut entanglement enough and space effectively shrinks. Add it and bridges grow. Geometry tracks information capacity. One more connection to thermodynamics. The first law of entanglement says small changes in entanglement entropy equal expectation changes in a modular Hamiltonian. In holography, that maps to linearized Einstein equations around a background. Translation: when you nudge the information content, the geometry responds as if obeying gravitational field equations. Gravity reads as elasticity of the entanglement fabric, the code's strain and stress relation. So where does this leave our goal? If reality is information, then the right question isn't what is it made of, but how is it encoded, transformed, and protected? That lens unifies horizons, arrows, and emergent locality under one roof. And yeah, it tempts the simulation story. But before we go there, let's separate a powerful metaphor from a common misread. The next step is to talk simulation theory, what it says, what it doesn't, and why it's often misused. Simulation theory, powerful but misused. You've probably heard the line, if future civilizations can run many ancestor simulations, odds are we're in one. That's Nick Bostrom's trilemma. He doesn't say we are simulated. He says at least one of these must be true. Civilizations die out before they're A-capable. They're A-capable but choose not to run many sims. Or they do run many, in which case most observers like us are simulated. It's a probability argument under specific assumptions, not a scientific detection. Hot take moment. If you had one falsifiable sim test, what would it be? Put it in the comments. We'll pick the sharpest to analyze on stream. Here's what often goes wrong. People treat simulation like a scientific claim with evidence behind it. Most versions are unfalsifiable. If you allow the simulator's arbitrary power to hide their tracks, any observation can be explained as they wanted it that way. That's not a testable theory. That's a narrative shield. Science needs risky predictions, places where the idea could fail. So what would count as a glitch? Folks point to cosmic rays aligned on a lattice, rounding errors in constants, or a hard cap on physical precision. The issue is expectations. A programmer might simulate with continuous math, not a pixel grid. Quantum theory itself sets precision limits via uncertainty and finite resources for measurement. Hitting those limits isn't evidence of code. If you saw Lorentz violations, preferred frames, or discretized dispersion relations in a way that matched a specific lattice model. That'd be interesting. So far, high-energy astrophysics and collider experiments haven't found robust, reproducible deviations that force a lattice picture. There are serious hints people bring up, like the idea that a simulated universe would show computational shortcuts or spectra consistent with finite grids. The problem is degeneracy. Many beyond standard model possibilities could create similar signals, and the cleanest tests keep coming up null. Also, even if nature is computable, that doesn't imply an external computer. Intrinsic computation, lawful state transitions, doesn't require a programmer. Now, this is important because there's a stronger claim worth taking seriously. Universe as computation is not the same as teens in a basement. Saying physical law implements computation is just recognizing that dynamics map inputs to outputs in structured ways. Cellular automata, Hamiltonian flows, quantum circuits, these are computations by evolution, not by intent. When we say it from qubit, we're talking about intrinsic information processing, not a GPU farm in base reality. Let me clear a common confusion with a micro story. Someone emailed me, if we're simulated, maybe the digits of pi eventually stop because the programmer used a lookup table. That mixes math with storage. Pi is a mathematically defined, provably infinite, non-repeating decimal in standard real analysis. If a simulation tried to fake pi with a finite table and you probed hard enough, you'd catch it, unless the sim upgraded or prevented the test. See the issue. With arbitrarily powerful sim managers, you can't pin down testable differences. Without that power, you risk detection. Either way, unfalsifiability lurks. A better way to frame it is constraints. If the world is a computation in the physical sense, it should obey resource bounds like Landwehr cost, error rates, and fault tolerance thresholds. That's exactly what we see. Thermodynamic costs to erase information, noise shaping quantum error correction, speed of light as a communication bound. These are features of physical law, not tells of an external coder. They anchor the informational picture without smuggling in mythology. There's also the ethics and agency angle. People sometimes use simulation talk to shrug off meaning. If it's a sim, nothing matters. That's a non sequitur. Experiences, suffering, joy, all are properties of states and relations. If a conscious system exists inside lawful dynamics, its experiences are real to it. Meaning lives in relations, goals, and consequences within the system. Whether the substrate is silicon, fields, or something else doesn't cancel value. Treating simulated as fake misunderstands emergence. Now can we search responsibly? Yes, by proposing concrete, falsifiable signatures tied to specific simulation architectures. For example, if spacetime were a cubic lattice at the Planck scale, ultra, high-energy particles might show anisotropic dispersion. If floating-point truncation affected quantum phases, we might see systematic decoherence biases. But these are hypotheses about specific discretizations, not about simulation in the broad sense. And current bounds are tight. Lorentz symmetry holds to extreme precision, and interferometers see no universal phase granularity at accessible scales. The real value of simulation talk is as a metaphor that pushes us toward information-centric physics. It nudges questions like, what are the code spaces of our universe? How is error correction implemented by entanglement? Where do fault lines in geometry appear as phase transitions in reconstructibility? Those lead to experiments, randomized measurements of entanglement, analog gravity setups, quantum teleportation, base traversable wormhole protocols in toy models, where we can actually test mechanisms. So here's the bottom line. Keep the philosophical argument where it belongs, interesting, provocative, and conditional. Don't mistake it for a shortcut around physics. The stronger, cleaner path is to add math, not programmers. Study how lawful information processing builds the world we observe. That moves you from speculation to predictions. And it leads directly to the question we opened earlier. If space is sewn by entanglement, can we watch the stitching in action? There's a sharper root than we're in a sim, and it runs through entanglement itself. Spacetime from entanglement. If reality runs on information, then the stitching of that information should look geometric. That's the bold move behind spacetime from entanglement. The idea is simple to say, deep to unpack. Patterns of quantum entanglement don't just live in space. They generate the shape and connectivity of space itself. Change the entanglement. You reshape the fabric. Quick poll. Team equals geometry from entanglement, or team entanglement rides on geometry. Vote with a comment. Let's see where you land. Start with equals a conjecture linking two famous acronyms. EPR is Einstein, Podolsky-Rosen entanglement. Two systems share correlations stronger than any classical story allows. ER is Einstein-Rosen, a wormhole, a non-traversable bridge between two regions of spacetime. The equals proposal says that maximally entangled pairs, at least in certain gravitational settings, are connected by tiny, non-traversable wormholes. No faster-than-light messaging, no sci-fi shortcut, just a geometric avatar of entanglement. The message is conceptual. Connectivity in quantum information has a geometric counterpart. Entanglement isn't sitting on geometry, it is geometry in disguise. Now, this is important because it gives you an intuition pump. Imagine dialing the entanglement between two big subsystems up and down. equals says you're thickening or thinning a geometric throat between their bulk regions. Push that intuition through add SCFT and you get a clear lever. Entanglement patterns on a boundary control minimal surfaces and therefore bulk distances. Geometry becomes a readout of correlation structure. But intuition needs tools and tensor networks step in. MERA, the multiscale entanglement renormalization ansatz, is a network that efficiently represents entangled states across scales. It looks like a tiling of tensors layered hierarchically, with disentanglers and isometries, removing short-range entanglement and compressing information as you flow upward. Draw MERA and you'll see a hyperbolic-like grid. That's not an accident. The network's geometry mirrors ADS-like spacetime. The vertical direction plays the role of scale, and geodesic-like paths through the network estimate entanglement entropies. When you cut the network to isolate a boundary region, the minimal cut length approximates the entropy, an echo of the Ryu-Takayanagi area rule. Here's where it gets interesting. In holographic quantum error-correcting codes like HAPPY, perfect tensors tile a negatively curved space to encode bulk logical degrees of freedom into many boundary legs. The code structure ensures that bulk operators can be reconstructed from multiple boundary regions, the redundancy that protects the spacetime from local noise. As you remove tensors, simulate decoherence or measurements, the network's ability to reconstruct deep bulk operators degrades. That looks like a horizon moving inward or space effectively shrinking. Cut enough entanglement, and a connected bulk snaps into disjoint pieces. That's a phase transition in geometry driven by information. Everything changes when you adopt the entanglement wedge perspective. Given a boundary subregion A, its entanglement wedge is the bulk region you can fully reconstruct from using the holographic dictionary. Increase entanglement across as boundary, and the wedge grows. Shrink either, and the wedge retreats. Two disjoint boundary regions can even own a common bulk bit via code redundancy. That's reconstruction as the definition of where something is. Location isn't absolute. It's a statement about which boundary data can recover which bulk operator. But wormholes and wedges still feel abstract. How do I get a practical grip? Use the cut intuition. Entanglement is like the number of bonds you must cut in a network to separate a region. More bonds mean larger minimal surfaces, which read as longer boundary bulk distances or bigger areas. Reduce those bonds by measurements, noise, or changing couplings, and distances grow, throats narrow, and eventually the network falls apart into islands. In quantum many-body experiments, you can witness cousins of this. measurement-induced entanglement phase transitions, where the state flips from volume law entanglement to area law, mirroring a switch from spacey to stringy connectivity. Now, microcausality and locality. How do local bulk interactions arise if the boundary is this global tangle? The code constrains which combinations of boundary operators reconstruct local bulk operators such that commutators vanish outside emergent light cones. Locality is a low-energy, redundancy-protected emergent feature. That's why you can have a quasi-continuous bulk even if the fundamental description is discrete tensors. The redundancy smooths out the jagged details, like anti-aliasing for spacetime. There's a delicate point about equals epr. It doesn't mean every entangled pair hides a literal wormhole you could jump through. Traversable wormholes require special couplings, like a carefully timed negative energy shock or double trace deformations, that effectively enable teleportation-like information flow consistent with causality. In toy models, SYK-JT gravity, teleportation protocols produce signals that behave as if they crossed a short-lived wormhole. The practical lesson isn't build a portal. It's engineer entanglement and interactions to route information through an emergent geometric channel. Let me add a pattern interrupt. What snaps when you overcut entanglement? Connectivity. In codes and networks, there's a threshold. Below it, bulk logical operators aren't reconstructible. Above it, they are. That binary jump is a geometric phase transition. In gravitational language, you'd call it a change in the dominant extremal surface or a topology change in the entanglement wedge. It's not fluff. It's a smoking gun that geometry is tracking information capacity. So practical intuition. Entanglement is the thread count of spacetime. High thread count smooth, connected fabric. Start cutting threads, rough patches, tiers, and isolated islands. That's why quantum weirdness can look classical. The code's redundancy and decoherence pick out stable local patterns, and it sets up the next puzzle cleanly. If space is sewn by entanglement, why does that quantum stitching present as the crisp, classical world you navigate every day? That's where decoherence takes the mic. Decoherence, why you don't see quantum strangeness. Quantum mechanics says systems can be in superpositions, this and that at once. So why don't you ever see a coffee mug smeared across the table and the floor? Because superpositions don't vanish, they get buried. The process is called decoherence. When a quantum system interacts with its environment, air molecules, photons, vibrations, it rapidly leaks phase information into those surroundings. Locally, interference becomes unobservable. You still have a global quantum state, but from your perspective, the weirdness looks gone. If this part made sense, you just unlocked why classical is a brilliant hack. Send this to the friend who says quantum is just vibes. Here's what actually happens. Think of a qubit in a superposition 1. Alone, it can interfere with itself. Couple it to an environment with countless degrees of freedom, and the joint state becomes entangled. E1, E1. If the environment states E and E1 differ even slightly across many particles, their overlap drops essentially to zero. When you ignore the environment, because you don't track trillions of scattered photons, the reduced state of the qubit becomes a mixture, not a coherent superposition. Interference terms vanish in practice. That's decoherence. Now, this is important because it explains why outcomes look classical without invoking a literal collapse. The environment selects stable pointer states, specific basis states that resist further entangling in a way that would mix them. For a dust grain, pointer states are roughly localized positions. For a current in a superconducting circuit, they're a distinct circulating states. These are the states that survive environmental monitoring. They're the ones that keep records, which is another way of saying they make sense as facts. The real secret is speed. Decoherence rates for macroscopic objects are absurdly fast. A micron-sized particle interacting with air or light decoheres in timescales like 10 - 20 seconds. By the time you blink, Every macroscopic alternative you care about has effectively lost coherence with its competitors. That's why you don't catch superpositions in the wild. You have to isolate and cool systems, use vacuum, and shield them to preserve coherence. Exactly what quantum experiments and quantum computers work so hard to do. Microstory to ground this. We set up a double slit with single photons and a very sensitive camera at the slits. With the camera off, you get a clean interference pattern on the screen, ripples of bright and dark where wave-like paths add and cancel. Turn the camera on so which path measures each photon, even gently, and the fringes vanish. Not because photons changed their mind, but because path information leaked to the detector. The environment learned something, and interference died locally. Now you might be thinking, so does decoherence solve the measurement problem? It solves a big chunk, the emergence of classicality, why we see definite-looking outcomes and stable records. It does not by itself pick a single outcome. The global quantum state still contains branches corresponding to different pointer outcomes. Interpretations diverge here. Many worlds says all branches are real and your experience rides one. Objective collapse models add new dynamics that truly select one result. Bohmian mechanics keeps a pilot wave guiding definite configurations. Decoherence is neutral. It's the common mechanism any interpretation must respect to match experiments. Why this matters for our story is the interface with information. Decoherence is environmental bookkeeping. The environment redundantly records information about certain variables, the pointer states, so multiple observers can sample different fragments and agree on what happened. That redundancy is called quantum Darwinism. It explains why facts become objective. They're the states that get copied widely without being disturbed. Objectivity is high-fidelity broadcast. Everything changes when you connect this to entanglement-built spacetime. If bulk locality is an error-corrected redundancy, decoherence is the process that selects the code words you and I can reliably access. The classical world is what the code protects, and the environment stabilizes. In holographic language, the pointer states are the ones whose information sits comfortably in entanglement wedges accessible to many boundary regions. That's why macroscopic cause and effect feels crisp. The reconstructible variables are precisely those with robust, redundant records. There's a practical payoff. By engineering environments, squeezed baths, dynamical decoupling, you can control decoherence, preserving quantum behavior longer. That's how we keep superpositions alive in ion traps or superconducting qubits. It's also why quantum sensors work. They're exquisitely sensitive to tiny phase shifts before the environment washes them out. Decoherence isn't only a nuisance, it's a tunable resource. One subtlety worth flagging. Decoherence doesn't require a conscious observer. It requires entangling interactions that spread phase information. A leaf under sunlight decoheres constantly. Your looking adds nothing special beyond being another environment fragment. Measurement is just controlled decoherence plus amplification to a macroscopic record. So what's the takeaway you should hold? You don't see quantum strangeness because the world is a superb copier of certain information and a relentless shredder of phase. Superpositions don't disappear, they become inaccessible. Classical reality is an approximation that's unbelievably good because the environment keeps it that way. Approximation brings clarity, and chaos brings arrows of time. And that's where we're headed next: entropy, memory, and why the past feels different from the future. Entropy, arrows, and the past hypothesis. Approximation brings clarity, and chaos brings arrows of time. Let's unpack that. Entropy is the measure of how many microstates fit a macro description. Low entropy means special, finely arranged configurations. High entropy means typical, scrambled ones. The second law says that for an isolated system, entropy tends to increase. Not by decree, but by overwhelming odds. There are vastly more disordered microstates than ordered ones, so random evolution almost always drifts toward the larger set. Personal prompt. What's one irreversible in your life you'd rewind if you could? That feeling maps to the physics here. Now, this is important because our sense of past to future tracks entropy gradients. You remember the past, not the future, because records are low-entropy structures created when interactions copy information into the environment. Writing a note, fossilizing a footprint, capturing a photo, all raise overall entropy while creating a localized, robust correlation. Radiation, diffusion, and friction point the same way for the same reason. They spread energy and information into more degrees of freedom. The arrow is statistical, not mystical. But there's a deeper question hiding underneath. Why does the universe start low entropy at all? If typical states are high entropy, you'd expect a featureless mess. Yet the early universe, hot, dense plasma, looks disordered, right? Here's the catch. For matter and radiation at fixed volume, sure, that looks high entropy. Bring gravity into the story and everything flips. Gravity's version of disorder is clumping. Black holes are the highest entropy objects for given energy and volume. A nearly uniform early cosmos is therefore extraordinarily low entropy in the gravitational sector. That's the loaded spring. This is the past hypothesis. The universe began in a very special, very low entropy macrostate. You don't have to specify every micro detail. You just assert a boundary condition that singles out an atypical start. From that boundary, the typical evolution is to higher entropy as structures form, stars ignite, black holes grow, and information gets dispersed. Our arrows, psychological, thermodynamic, radiative, line up because they all piggyback on that gradient. Coarse graining is the bridge between microlaws and macro arrows. Take an astronomical number of microstates and summarize them with a few variables: temperature, pressure, density. Coarse grain differently and you can flip what increasing entropy looks like. But the macroscopic variables we actually use are the ones that are stable under interactions and easy to read out, pointer-like at scale. That practicality explains the universality of the arrow. Many choices of coarse graining converge on the same trend in a universe with that special start. Where does decoherence fit? It's the mechanism that makes records durable. When a system interacts with its environment, phase information disperses. In return, specific classical-looking correlations become redundantly encoded. That redundancy is a one-way street in practice. You can, in principle, reverse a small, well-isolated quantum system and recohere it. For macroscopic situations, the information has radiated into astronomically many degrees of freedom. The cost to gather and phase align all of them scales beyond imagination. So we get practical irreversibility, the kind your coffee knows. Cosmology adds texture. As the universe expands, horizons appear. There are regions you can't communicate with within finite time. Horizons hide information, and hidden information reads as entropy. Black holes give the sharpest version, area counts microstates, but cosmological horizons carry entropies too. That feeds back into arrows. As accessible regions change, so does where information can flow and be stored. Gravity doesn't break the second law, it extends it with new bookkeeping. Now the puzzle everyone hits. Why was the beginning so ordered? Several ideas compete. Maybe there's a dynamical bias that funnels states toward low gravitational entropy initially, like certain inflationary scenarios suggest. Maybe there's a deeper principle or measure that makes simple geometry at the start overwhelmingly likely. Or maybe, modestly, the past hypothesis is a boundary condition we accept for now. The way we accept this is the state in the lab and ask, what follows? Theories differ, but the empirical payoff is clear. Starting low explains the aligned arrows we observe. Here's where the holographic angle can help. If fundamental descriptions live on boundaries, initial conditions might be simpler to state as constraints on boundary data. Specific entanglement patterns, symmetry charges, or state purities that force a smooth, nearly uniform bulk. In AD-SCFT, pure, low-complexity boundary states correspond to simple bulk geometries. Crank up complexity and you grow interiors, excitations, and eventually black holes. That suggests a path. Early universe simplicity as low boundary complexity, late-time richness as the growth of complexity and entanglement. Practical upshot for you. Your experience of time's flow is thermodynamic. Memory, cause, aging, and even why you can crack an egg but not uncrack it, these ride the entropy gradient seeded by that special start. The microlaws don't know which way is forward. The boundary condition and the coarse-grained variables do. And once you see that, a bolder thought lands. Maybe gravity itself is a thermodynamic response of the information fabric to changes in entanglement and energy. But there's a deeper twist waiting. If the arrows come from statistics and horizons count information, what if the field equations of gravity are nothing more than equations of state for that information? That's not poetry. There's a derivation that points exactly there. Gravity may be emergent thermodynamics. Let's walk straight into it. Gravity as emergent thermodynamics. Here's the leap. What if Einstein's equations aren't fundamental laws but equations of state, like PV equals nRT for gases, summarizing deeper microscopic statistics? That's the punchline of Ted Jacobson's 1995 result. He started with two inputs. First, horizons have entropy proportional to area. Second, accelerated observers see heat, the UNRA temperature. Then he asked for local thermodynamic consistency. If energy flows across a local Rindler horizon, the Clausius relation delta Q equals TdS must hold. From that single demand, out popped the Einstein field equations. No extra magic, just thermodynamics pressed against causal horizons. Hit like if delta Q equals TdS right arrow Einstein just rearranged your mental furniture. Now, this is important because it flips the usual direction. We didn't assume curvature causes acceleration to feel hot. We assumed heat and entropy laws are universal and derived curvature dynamics. If entropy density per unit area is fixed, 1/4 per Planck area, then requiring local energy conservation, and the equivalence principle forces spacetime to respond exactly as general relativity dictates. Gravity becomes the elasticity of an information-bearing medium. Change the informational content crossing a horizon, and geometry springs to accommodate. UNRA temperature is the second pillar. An observer with constant acceleration experiences a thermal bath at temperature T equals h/2 pi c kb, even in empty space. That's a pure kinematics plus quantum effect. What counts as vacuum depends on your motion. Combine that with the Bekenstein-Hawking area-entropy relation, and you've got temperature and entropy tied to horizons everywhere, not just black holes. If every local patch of spacetime has an associated horizon for some accelerated observer, thermodynamics is baked into geometry at every point. Everything changes when you add entanglement. The first law of entanglement says that for small perturbations around a reference state, the change in entanglement entropy equals the change in expectation value of the modular Hamiltonian. In holographic setups, that translates to linearized Einstein equations around AdS. In plain language, nudge the information content, and the metric adjusts as if obeying gravity's field equations. That's not coincidence. It's the same thermodynamic logic seen through an information lens. So what's the medium? Not atoms of space in the classical sense, but degrees of freedom organized by quantum entanglement. Think of geometry as an emergent elastic solid whose strain is curvature and whose stress is energy momentum. Pull on the entanglement, change who's correlated with whom, and you warp distances. Dump energy through a horizon and the entropy budget shifts, the fabric flexes. In this view, the Einstein tensor is the constitutive relation of that medium. The way Hooke's law relates stress and strain for a crystal. Let me ground this with the local picture Jacobson used. Take any point and slice spacetime into tiny neighborhoods. For any small space-like patch through that point, there's a local Rindler horizon for observers accelerating just right. If energy delta Q crosses that horizon, the observer registers heat. If horizon entropy is area 4, then TdS must equal delta Q. Demand this equality for all such observers and all patches, and the only way to make it work is if the Ricci curvature relates to energy momentum in exactly Einstein's form, plus a cosmological constant popping out as an integration constant. Gravity appears as the only thermodynamic response consistent with those horizon bookkeeping rules. But wait, does this mean quantum gravity is just thermodynamics? Careful. It means the macroscopic equations of spacetime behave like thermodynamic equations of state. Just as thermodynamics doesn't tell you water molecules are H2O, stat mech does, the Einstein equations don't tell you the microstructure. They constrain it. The microtheory could be strings, loops, tensors, or something we haven't named. What's robust is the thermodynamic facade. Horizons have entropy, acceleration c heat, geometry and energy talk through delta Q equals T ds. Here's where the entanglement first law tightens the story. In add SCFT, small boundary state changes shift quantum extremal surfaces, altering their areas. Those area changes track boundary entanglement changes, which, via the dictionary, must match bulk energy fluxes. The linearized Einstein equations are the consistency conditions that keep all those pieces aligned. Move away from linear response, and you get nonlinear geometry responding to large information reconfigurations, black holes forming, wormhole mouths fattening, interiors growing with complexity. Unruh's effect also clarifies why vacuum isn't empty. Vacuum is full of correlations. Slice it with a horizon and you split entangled pairs. An accelerated observer loses access to half and reads a thermal state. That missing information is entropy. That entropy's gradient drives an effective force, the same way temperature gradients drive heat flow. In this framing, inertia and gravity blur. Both emerge from how observers interact with vacuum correlations and how horizons hide information. Let's hit a practical implication. If gravity is elasticity of entanglement, then changing the entanglement structure, by measurements, couplings, or dynamics, should shift effective geometry. We see analogs in toy models, tweak tensor networks or induce entanglement phase transitions, and reconstructible bulk, regions swell or collapse. In continuum language, it predicts that consistent changes in modular Hamiltonians map to predictable curvature responses. That ties experimental probes of entanglement, randomized measurements, tomography, to gravitational statements in lab analogs. One more layer. Equations of state can fail near critical points. If spacetime is a medium, then extreme regimes, Planckian densities, early universe singularity approaches, might be where the equation of state picture breaks and microstructure shows. That's not a bug, that's an invitation. Just like superfluid helium reveals quantum underpinnings when classical hydrodynamics fails, quantum gravity's microdegrees should announce themselves where thermodynamic gravity stumbles. So if the equations are equations of state, spacetime isn't fundamental. It's the coarse-grained description of an informational medium whose microstructure we're slowly decoding. Okay, so what's actually fundamental? The math keeps pointing at symmetries and the relations they enforce, the structures that stay put while our pictures change. And that's where we turn next. Gauge freedom, duality, and what ought to count as real. Symmetry, duality, and what counts as real. Okay, so what's actually doing the heavy lifting underneath all these pictures? Symmetry. Not as decoration, symmetry as constraint. When physicists say gauge symmetry, we're talking about a redundancy in our description. Multiple mathematical configurations represent the same physical situation. Change the gauge, nothing observable changes. That should instantly make you cautious about reifying the variables we write down. Some of them are bookkeeping, not Beebles. Take electromagnetism. We write a vector potential mu, but only the field strengths E and B show up in forces. Shift mu by a gradient and the physics stays put. The potential is useful, sometimes essential. Hello, Aharonov, Bohm phases, but it's not uniquely determined by reality. The same theme runs through non-abelian gauge theories, SU2, SU3. We pick gauges to compute, then strip the gauge away when we talk about observables. So which parts are real? The relations that survive gauge transformations, the gauge invariant structures, earn that title. Now, this is important because it connects directly to duality. A duality says two very different-looking theories describe the same physics. Add SCFT as one, but there are many. Electric, magnetic dualities that swap strong and weak coupling, T-duality in string theory that flips big circles with small ones, mirror symmetry trading complex geometry for symplectic geometry. When two formalisms make all the same predictions for all observables, you don't have two worlds. You have two coordinate systems on one world. Everything changes when you embrace that. If two maps are equivalent, the specific stuff each map talks about, brains here, fields there, can't be fundamental by itself. What's robust are the patterns, spectra, scattering amplitudes, correlation functions, symmetry algebras, anomaly coefficients. Those are the invariants. So when we ask what counts as real, a clean answer is structural realism, the relational structure encoded by symmetries and observables, not the picture-specific furniture. Let me show you a familiar trap. In quantum field theory, you can describe the same physics in terms of particles or in terms of fields. At low energies, particles are an excellent language, sharp peaks in detectors, tracks in chambers. Crank up the energy or change the background, and the particle concept becomes fuzzy. The field description keeps going. Switch to a strongly coupled regime, and even fields feel clumsy. A dual description in terms of strings or monopoles might be clean. The ontology that feels obvious is wearing energy scale glasses. Gauge symmetry sharpens the point. We often talk about the electromagnetic field at a point, but in quantum theory, strictly local gauge invariant observables are rare. What's really measurable are extended objects, Wilson loops, phase factors picked up by charges looping in space, line and surface operators in non-abelian theories. Those integrals are gauge invariant. They're a-relational, comparing phases around a path, not absolute. Reality shows up in relations across regions, not in isolated values at points. Here's a quick micro story. A colleague once insisted a certain potential configuration must be real because his simulation crashed when he changed gauge. When we checked, the crash was a boundary condition bug. His code fixed the gauge at one edge and floated at the other. Once we patched the boundary conditions, every gauge worked and his real vanished. Lesson: if changing descriptions leaves observables intact, don't marry the coordinates, marry the invariants. Conscious experience in a non-fundamental world. So where does this leave you, the person having experiences inside all this structure? Start with a sober claim. Your perceptions are models. The brain isn't a passive camera. It's a prediction engine constantly guessing what's out there and updating those guesses with sensory error signals. That's predictive processing in a nutshell. You don't perceive raw reality. You perceive the brain's best current hypothesis that keeps incoming errors low. Quick reflection. What prediction did your brain get hilariously wrong this week? That's your model showing its seams. Now, this is important because it explains why solidity and continuity feel non-negotiable. Your brain bets heavily on stable, low-noise variables, surfaces, objects, faces, trajectories, because those predictions pay off. They're the macroscopic pointer states of everyday life, robust, redundantly recorded, and cheap to track. The model that says this table is solid and here has tiny prediction error. The model that says a fuzzy superposition cloud might be here would drown in error signals. Your brain ruthlessly prunes it. The real secret is control. Perception isn't just about describing, it's about acting to keep predictions reliable. You move your eyes to reduce uncertainty. You reach out to test weight. You tilt your head to disambiguate a sound. Action improves the model by harvesting better data. That's why the world feels actionable first and theoretical second. The brain prioritizes variables that support control, grip, balance, timing, over micro-accuracy about quantum details that never help you catch a ball. But if the universe is emergent, is consciousness an illusion? Careful with words. Illusion doesn't mean non-existent. It means not what it naively seems. Pain, color, and the feeling of flow are real experiences implemented by neural dynamics in bodies embedded in environments. Calling them just brain states under cells how layered those states are. Biophysics, network motifs, learning history, embodiment, social scaffolding. Emergence here is richness, not dismissal. Let me give you a sketch of the machinery. The cortex runs hierarchical generative models. High-level priors about causes send predictions down. Lower levels send back mismatches. These loops run at multiple timescales. Slow loops track identity and goals. Fast loops track edges and tones. Conscious access likely rides the global broadcasting of certain contents across widespread networks, the frontoparietal workspace idea in one camp, or the formation of specialized integrative complexes in another. Either way, access correlates with coordinated metastable patterns that can influence many systems at once: memory, action, language. Now you might be thinking, do we need quantum brain magic to explain any of this? There's no good evidence. Neurons are warm, wet, and noisy. Microtubule coherence won't survive decoherence at body temperature at scales relevant to cognition. Quantum affects matter in chemistry and sensing niches, but current neuroscience explains perception, learning, and attention with classical stochastic dynamics on networks. That doesn't close the door on subtle quantum roles. It just says the bar for quantum mind claims is high and not met yet. So why does solidity feel so convincing? Because it's tied to the code the environment stabilizes. When you and I look at a cup, zillions of photons redundantly record the cup's shape and position. Many observers can sample different fragments of that light and agree. Your brain learns that redundancy means real and shareable. Strip away redundancy, dim light, noise, unfamiliar contexts, and confidence drops. The feeling of reality tracks the density of consistent records you can access. Here's a micro story. Someone DM'd me about déjà vu after reading about entanglement. They wondered if déjà vu was quantum memory leakage between branches. A cleaner story. Déjà vu likely arises when recognition circuits fire before contextual tagging completes, producing a false sense of prior occurrence. The brain's timing jitters. The model confuses familiar pattern with "we've been here." No multiverse needed, just predictive machinery with occasional misfires. Ethically, this reframing helps, not hurts. If experience is the flow of structured information in a living system, then minimizing suffering and enabling flourishing are about altering dynamics, resources, relationships, learning environments, to change trajectories of experience. Meaning lives in goals pursued by agents within a world of constraints. None of that evaporates if spacetime is emergent. If anything, it focuses attention on what we can shape: models, interactions, and feedback loops. What about the hard problem? Why there's something it's like? Theories diverge. Some say consciousness is identical to certain information processing structures when integrated in specific ways. Others argue experience is fundamental or that our concepts are confused. Here's the disciplined move for our path. Keep the physics honest, don't smuggle metaphysics as data, and stick to claims that tether to prediction and intervention. We can map neural correlates, manipulate contents, and chart how access arises, while staying neutral on ultimate metaphysics. Let's connect back to unreality without nihilism. Calling the universe not fundamental doesn't make it flimsy. It means our best high-level variables, objects, fields, even time, are effective descriptions that compress deeper relations. Your conscious life runs on those effective variables. Their reliability is why you trust steps, contracts, and friendships. The map is emergent and still actionable. So here's the bridge forward. We've said space can be sewn by entanglement, time can be relational, gravity can be thermodynamic, and experience can be predictive modeling stabilized by redundancy. That's elegant, but can any of it bend under experiment? We promised one experiment that makes the story tangible. It's not a sci-fi reveal. It's a precise setup where information, geometry, and quantum dynamics meet and leave a measurable mark. Let's close the loops we opened. The one experiment that bends reality. We promised one experiment that makes this whole story tangible. It's not one device. It's a family of tests where information, geometry, and quantum dynamics collide and leave measurable traces. Think of this as a reality stress test. Push on information, watch spacetime flinch. If you could run one of these tomorrow with an unlimited grant, what would you build first? Your answers guide our next lab collab. Start with black hole analogs. You can't put a Schwarzschild hole on a bench, but you can create horizons for waves in lab media. In Bose, Einstein condensates, fluids, and optical fibers, researchers engineer regions where excitations can't escape, an effective event horizon. What do you look for? Hawking-like radiation. Pairs of excitations created near the horizon, one trapped, one escaping, with a thermal spectrum tied to the horizon's effective surface gravity. Experiments have seen spectra consistent with this, and even correlations between partners. That correlation is the tell. It's entanglement across a horizon, the same ingredient that sets black hole entropy and powers the holographic story. If horizons anywhere cough up paired thermal quanta, horizon thermodynamics isn't just a metaphor. Now teleportation through a wormhole, careful. In toy models like SYK and its low-energy JACU, Teitelbaum gravity dual, there's a protocol. Entangle two systems, couple them briefly in a precise way, and send a quantum state. The signal emerges on the other side as if it passed through a short-lived, traversable wormhole. It's not sci-fi. It's a controlled interference pattern produced by coupling the two boundaries. Google's and Caltech's teams ran circuit versions of this idea in small quantum processors, observing signal transmission with properties that match the gravitational calculation. The key isn't the gimmick, it's the mechanism. You arrange interactions that transform just entanglement into a geometric channel. That's information rooted by engineered correlations, behaving as a wormhole in the dual description. Entanglement tomography is the quieter star. The claim, geometry equals entanglement, risks hand-waving unless you can infer shape from data. With randomized measurements and classical shadow techniques, you can estimate entanglement entropies and mutual information across many partitions of a quantum many-body system. Feed those into reconstruction algorithms inspired by minimal surface geometry, and you can recover a coarse bulk connectivity graph. What region sits close to what, where the throats are thin or thick. Groups have already mapped entanglement phase transitions, where connectivity suddenly reconfigures as they tune measurement rates or interaction strengths. That's a bulk snap detected by boundary statistics. If you can dial entanglement and watch the inferred geometry morph, you're not describing space, you're building it. Precision quantum clocks bring time into the lab. Put two optical clocks at slightly different heights, and they tick at measurably different rates due to gravitational redshift. We've done this over centimeters. Push to quantum superpositions of clocks, and you test superpositions of time dilation, subtle signatures predicted when gravity and quantum meet. These experiments aren't about catching the absence of time. They're about quantifying how effective time emerges and bends in regimes where entanglement and gravity talk. When a change in relational information, who's entangled with whom, shifts a clock's phase, you've measured the cost of time as information flow. Let me give you the micro story. I visited a photonics lab where they drive light through a fiber with a moving refractive index front and optical horizon. Detectors click in the dark. Not noise, a spectrum with the right slope and cross correlations between modes on opposite sides. You stand there hearing the click stream and realize the vacuum isn't empty. Horizons, even synthetic ones, rearrange access to correlations, and the energy budget pays out as quanta. That's delta Q equals TDS showing its face in a cable. What would actually falsify the holographic picture today? Not no ADS. We already know cosmology isn't ADS. You'd look for consistent violations of area law entanglement scaling in ground states where it must hold. Breakdowns of modular flow predictions that tie small entanglement changes to stress energy. failure of bulk reconstruction redundancy in codes that should protect it, or precise, reproducible Lorentz-violating lattice signatures sold as simulation, but incompatible with high-precision bounds. On the positive side, you want converging evidence. Wormhole teleportation protocols scaling to regimes where semi-classical gravity is a better approximation. Analog horizons showing entanglement partner correlations with increasing fidelity. Entanglement tomography on programmable quantum simulators recovering bulk-like connectivity that tracks theoretical extremal surface switches. There's a bigger ambition: marry tomography with dynamics. Prepare a state, map its entanglement shape, quench it, change coupling suddenly, and keep mapping as it evolves. If the bulk picture is right, you should see wavefronts in information. The growth of entanglement behave like light cones in an emergent geometry, with velocities capped by Lieb-Robinson bounds. When extremal surfaces jump, your inferred bulk should flip to a new topology of wedges. If, in parallel, a gravitational calculation on the dual predicts those jumps at the same parameter values, you've caught geometry in the act of following information. One more testbed: measurement-induced transitions. Hybrid quantum circuits, alternating unitary gates with projective measurements, show sharp shifts between entangled and disentangled phases as you tune measurement rate. That's an information bottleneck you can control. The holographic translation says, cross the threshold and space fractures. Watching entanglement negativity and mutual information reorganize across that threshold, then reconstructing connectivity, is like filming a bridge collapse and rebuild in the bulk. So does any single experiment prove unreality? No. Science rarely grants silver bullets, but this cluster of tests already bends the story. Horizons radiate thermally with entangled partners, traversable wormhole, like protocols route information as predicted. Geometry tracks entanglement capacity. Time dilation shows up at quantum precision tied to relational structure. Each result is a brick. Together, they build a case that information is the driver and geometry is the readout. And that brings us to the honest question we opened. With all this in hand, does the universe exist? The next part gives you the straight answer, grounded, not mystical. So, does the universe exist? The honest takeaway. Here's the straight answer. The universe exists the way a great map exists: robust, predictive, insanely useful, and not the bottom layer. Spacetime, particles, even time itself behave like effective variables that compress deeper structure. They're real as emergent facts, the way pressure and temperature are real, even though no single molecule has them. If this gave you a cleaner frame for what's real, save and share. Someone in your group chat needs this sanity check. Now, this is important because it resets the stakes. Saying not fundamental isn't a demolition, it's a demotion. The map works because the underlying information fabric enforces consistent constraints, symmetries, conservation laws, error-correcting redundancy. That's why rockets hit targets, GPS syncs clocks, and colliders find the predicted peaks. The picture holds together because the code underneath is tight. The payoff isn't philosophical wordplay. It's new predictions and new tech. If geometry responds to entanglement, then measuring and steering entanglement should let us shape effective dynamics, better quantum sensors, communication rooted through engineered correlations, analog gravity platforms that benchmark quantum gravity ideas. If gravity is thermodynamics of information, we can translate gravitational puzzles into statements about entropies, modular flows, and error thresholds that lab systems can probe. That's a research program, not a slogan. So where does that leave existence? Think of layers. At the microlayer, there are quantum states and relations, the web of amplitudes and entanglement constrained by symmetries. From this, spacetime appears, a smooth local arena when entanglement is dense and well-patterned. On top of that, matter fields and quasi-particles emerge with effective masses and charges. Higher still, chemistry, biology, brains, and cultures, structures stabilized by decoherence and redundancy. Each layer is as real as its ability to make stable, compressible predictions within its domain. That's the kind of reality you bank on every day. You might want a single what it really is answer. Dualities crush that hope productively. When two very different descriptions match all observables, ontology has to loosen its grip. What survives are invariant structures, spectra, S-matrices, entropic relations, algebraic symmetries, causal cones. Structural realism isn't dodging the question. It's answering the part we can test, and it keeps winning. There's a human question here. How do you live with a non-fundamental world? First, replace certainty with curiosity. Treat models as tools you can swap when the job changes. Second, track the invariants. What stays fixed when you change perspective? Third, separate meaning from metaphysics. Value lives in experiences, goals, and consequences within the system. Whether the substrate is fields, qubits, or unknowns doesn't dilute the stakes of kindness, honesty, and exploration. What about the biggest risks to this picture? If entanglement first reconstructions fail systematically where they should work, if modular flow predictions repeatedly miss, if horizon thermodynamics breaks in regimes where it should apply, then it from qubit would need surgery. That's good news either way. A wrong path with precise failures teaches faster than a fuzzy right path. We're already threading experiments to find those pressure points. One more subtlety. Emergence isn't magic, it's compression with guarantees. The guarantees come from symmetry, scale separation, and error correction. Break those and the layer above wobbles. That tells you where to push. Near critical points, universality kicks in and the details of the micro fade. Far from them, details matter. In quantum gravity terms, semi-classical geometry is a universality class. At Planckian edges, expect the class to fracture and the microstructure to speak up. So does the universe exist? Yes, as an effective world whose laws are astonishingly accurate summaries of a deeper informational order. No, as an ultimate indivisible stage set. The map is breathtakingly good and still a map. The cleanest way to hold this is simple. Reality is what resists you when you try to change it. Effective layers resist reliably. That's enough reality to build, navigate, and wonder. If that clicked, the next move is obvious. Keep following the constraints, keep measuring the information, and keep trading pictures for predictions. The path forward isn't worshiping one metaphor. It's testing many and keeping what pays rent in data. Here's the takeaway. What you call the universe is a model that works astonishingly well, but it's likely not the bottom layer. If this helped reframe reality, subscribe and stick around. Watch next, my breakdown on black holes, entanglement, and information. Drop your biggest reality glitch in the comments, I read them, and tell me what experiment you'd run to test this. If you learned one new idea, send this to a friend and ask them to explain it back. Teaching locks it in. Quick glossary moments. Entropy, a measure of how many microscopic arrangements fit the same macroscopic description. Low entropy means special, finely tuned configurations. High entropy means typical, scrambled ones. The second law says entropy tends to rise because overwhelmingly more states live in the high entropy set. Unitarity. In quantum theory, evolution preserves total probability. Think of it as information conservation in closed systems. No quantum data gets lost. It only moves around and entangles. That's why black hole information puzzles matter. They test whether unitarity holds in gravity. Decoherence. When a quantum system leaks phase information into its environment, interference becomes locally unobservable. You still have a global superposition, but practical access to the phase is gone. It explains why the world looks classical without invoking a special collapse. Duality. Two very different theories make identical predictions for all observables. They're different coordinate systems on the same physics. Add SCFT is the flagship example. Gravity with one extra dimension equals a non-gravitational quantum theory on the boundary. Entanglement. Quantum correlations that can't be explained by shared classical randomness. Measure one part and you instantly learn something about the other. No signaling required. In our story, entanglement isn't just correlation in space, it organizes space. Holographic principle, the claim that all information in a volume can be encoded on its boundary, with 1 bit per roughly Planck area unit. Born from black hole thermodynamics, where entropy scales with area, not volume. Ryu Takuyanagi, RT surface. In holographic settings, the entanglement entropy of a boundary region equals the area of a minimal surface in the bulk anchored to that region. It's the geometry, information dictionary at work. Entanglement wedge, the bulk region reconstructible from a given boundary region using the holographic code. If an operator lies in your wedge, you can recover it from your boundary data. Quantum error-correcting code, a scheme that encodes logical quantum information into many physical degrees of freedom, so it survives local noise. In holography, this structure protects bulk data from boundary disturbances and explains redundancy in reconstruction. Landor's principle, erasing 1 bit of information has a minimum heat cost of kT ln2. Information processing isn't free, it's tied to thermodynamics. That's why information is physical isn't a metaphor. Unruh temperature. An accelerated observer perceives the vacuum as a thermal bath with temperature proportional to acceleration. Horizons and heat go hand in hand, even without black holes. Wheeler-DeWitt, a quantum gravity equation where the total Hamiltonian annihilates the state, h psi equals, reflecting the absence of an external time. Time emerges relationally inside the state. Page, Wooter's mechanism, a way time can emerge from correlations with an internal clock subsystem. Conditional states evolve even when the global state is timeless. Equals Epper conjecture, a proposed link between entanglement EPR and non-traversable wormholes ER. It encodes the idea that quantum connectivity has a geometric avatar. Modular Hamiltonian first law, a formal generator tied to a subsystem state. Small changes in entanglement entropy match small changes in its expectation value. In holography, this reproduces linearized Einstein equations. Keep these in your back pocket as handles. If a claim sounds abstract, ask, which of these tools does it lean on? Pacing and retention inserts. Quick check-in, would you keep watching right now? If not, here's the mini reveal. When we measured gravitational redshift with tabletop optical clocks over centimeters, we watched time differ across the height of a coffee mug. That's relativity landing on the lab bench. If this surprised you, comment coffee clock so I know you saw it. You probably think simulation is science because it sounds technical. Pattern interrupt. Unless it risks a concrete prediction, it's not physics, it's fan fiction. The math-first route gave us RT surfaces we can estimate from experiments. That's testable. Smash like if you're here for receipts over rhetoric. Prescripted objection. If space is entanglement, why don't we just rewire space in the lab? Short answer. We already do in toy forms. Tune measurement rates in hybrid circuits and watch connectivity snap, a geometric phase transition you can plot. Would you want to see that demo on the channel? Say rewire space and it'll prioritize it. Energy shift. Here's a micro story we didn't tell. Last month, someone asked if Lorentz violations in gamma ray bursts prove a lattice. The data, within bounds that keep special relativity intact. The 30-second rule says give you a payoff, so here it is. If a preferred frame existed at accessible scales, we'd have seen dispersion anomalies by now. We haven't. Bookmark this for your next physics debate. Preview of what's coming in the watch next video. We'll take the black hole information paradox, show you the page curve, and explain how unitarity survives without breaking causality. One graph, 2 aha moments. Turn on notifications so you don't miss it. Another objection. Decoherence sounds like sweeping the measurement problem under the rug. Clarify. Decoherence isn't a rug, it's the floorboards. Any interpretation must pass through it to match data. What differs is what you think lies under the floor. If you want a full series on interpretations, type Interpretation Series below. Pattern interrupt, number to remember, 10-20. That's how fast macroscopic decoherence can hit a micron particle. If you blinked, you missed 1 trillion of those. Surprising revelation. Wormhole teleportation experiments aren't teleporting humans. They're routing qubits so the correlators match gravity predictions. The significance is that 2 languages, circuits, and geometry line up on the same outcome. If that blew your mind a little, send this to the skeptic in your group chat. Prescripted objection. If gravity is thermodynamics, does that make it less real? Think of pressure. You can do real work with it. It's emergent and it moves pistons. Emergent doesn't mean optional, it means compressed. Momentum keeper. Remember the claim that horizons radiate. Analog horizons give you partner correlations. The smoking gun that it's entanglement driven, not just thermal noise. That's the detail that converts metaphor into mechanism. Mini preview to keep the loop open. When you hear page, wooters, think time from a clock entangled with the system. In the next deep dive, we'll build a toy version with 2 qubits so you can see time tick with no t in the equation. Direct question to re-engage. If you could dial one variable, entanglement density, measurement rate, or symmetry constraints, to reshape an emergent geometry, which would you pick and why? Drop it in the comments. I'm mining those for the lab demo. Final pattern interrupt. Reality isn't less real because it's layered. It's more powerful because each layer gives you levers. Physics is about finding the levers that pay rent in predictions. Keep your eye on those and the rest follows. If you made it here, comment lever found so I can thank you personally in the next video.